Hello everyone. Our group is Group 7 and our topic is quantum light interacting with beam splitters and interferometers. So first of all, what is quantum light? In our project, we are mainly dealing with single photon light source. So that is our quantum light in this case. And my, okay, I forgot to tell one thing. My name is Rohit and I'll be covering the single photon light source part. Okay, so now there are two main topics in this heading, beam splitters and interferometers. So what is a beam splitter and what are interferometers? So beam splitter is basically an optical device which splits light into two paths in simple words. And what is an interferometer? Well, we have used interferometers in our lab, like in a previous lab in third semesters also, like Mark Zender interferometer, we'll be using that interferometer in the coming. My colleague will be using discussing that. Okay, so what is an interferometer? Interferometers also uses beam splitters as its components, and interferometer is basically an optical instrument that splits a beam of light into two or more paths, directs them along different paths, and then combines them and then interferes them. And we see bright and dark fringes on the screen. If I make a diagram of MZH interferometer, so it looks basically like this. We have two beam splitters, we have two mirrors, we have detectors here. We have incoming light, splitter one, beam splitter two. So basically what happens is light goes here, it splits from beam splitter, reflects from the mirrors, again splits from beam splitters, combines at these two detectors, and we see interference patterns. Okay. Now there was a famous experiment that was done with single photon or so. So Taylor in 1909 did an experiment with a highly attenuated beam of light. Okay. And at these attenuation levels, he saw interference pattern. So what he concluded that the source was emitting single photons, and these single photons were interfering with themselves and showing interference fringes. So he was wrongly concluding that his source was producing single photons, because as we know, as we have learned in the class, his source was a chaotic source, and chaotic source generally produces light in bunches of photons. To produce uh, to produce single photon, we need something called anti-bunching or anti-bunched photons. So he was wrongly concluding that his source was an anti-bunched source. And Dirac famously said, each photon interferes with itself. Interference between two photons doesn't occur. Okay. So now comes grandeur. Okay. Granger and others, they did their experiment in 1986. They produced a true single photon source. So what they did was simply amazing. They took a calcium atom and excited it to some state. The calcium atom was excited to some high S state. So here is a calcium excited state. Now, when it goes to excited state, there are two metastable states, this one and this P state. So it comes back to the P state, emitting new one, and after some time, it comes to ground state, emitting mu 2. And these two photons were emitted in opposite directions to conserve momentum. So now the Granger experiment will be discussed in more detail by Ashraf, but I can tell some details about this experiment. So the photon nu one was basically used as a trigger for some gating mechanism. It tells basically two detectors that get ready, there is another photon coming, that is mu2 is coming. Okay, so what would have happened? A single photon mu2 was coming, and classically it would have been split into two parts due to the beam splitter, and detectors the two detectors would have simultaneously goes off. We would have detected some coincidence here. But quantum mechanically, what they observed was something different. They observed that only one detector at a single time. There was no coincidence between the photons. And this famous experiment was also called anti-correlation experiment of Granger, because there was no correlation between the photons. So there were two famous conclusions from this experiment. Conclusion of Granger experiment. The first was photons are indivisible, because if they were indivisible, they were divisible, then we would have detected two photons simultaneously at the two detectors, but we didn't. So we conclude that they are indivisible. And the second thing that we confirmed from this was that light is quantum in nature. Okay, so that's it for my part. Beam splitters next.
So, hi everyone. My name is Amit Yadav, and I'm going to discuss quantum mechanics of beam splitters. So, for coherent lights and thermal beams, the quantum and classical treatment of beam splitters agree, both agree. For but for both, for single photon or a few photons, let me put a new page. So, for coherent light beams, right, and thermal beams, both classical and quantum, and treatment of beam splitters acting. So but for single photon or few photons. For few photons, classical treatment of beam splitter produces misleading results. Okay. So first of all, we will see how classical treatment is giving wrong results. So for that, assume this is a beam splitter. This is incoming incident light having A1, E1. This is reflected A2, E2, and this is transmitted A3, E3. So E1, E2, E3 are for classical treatment with classical A1 cap, A2 cap, and A3 cap are for quantum. So our beam splitter is lossless beam splitter. So and let me clear. So R is reflectance, T is transmittance, T is transmittance. So E2 is E2 is R E1 and E3 is T E1. And our beam splitter is lossless. So incoming intensity is equals to outgoing intensity. From here we will get uh, E square is equals to mod of R square E1 square plus mod of theta square E1 square. That will give mod of R square plus mod of T square is equals to 1. This is complete classically. So for quantum mechanics, let E1 is represented by annihilation operator. Annihilation operator A A1 gap. Similarly, EI is equals AI replacing AI annihilation operator I is equals to 1, 2, and 3. So here A2 cap is equals to R A1 cap, A3 cap is equals to T A3 cap. So as we know from quantum mechanics, Aij from quantum mechanics we know that commutator relation AI with Aj dagger, that is del Ij Aij Ai Aj, that is 0 is equals to Ai dagger Aj dagger, both are 0. So uh, we will see this for A2 A2 dagger. This will give R A1 R star A1 dagger, that will give mod of R square, or this must be equals to 1. Similarly for A3 dagger, this is dagger, this will give R A, sorry, T, 1 minute. Okay, so this is T A1, comma T star A1 dagger. This will give mod T square, that is equals to 1. Let me mark this is equation 1. This is equation 3, this is equation 2. Uh, 4. A2, A3 taker. This will give R A1 T star A1 taker. This will give RT that is not equals to 0. This is equation 4. So from equation 1, mod R square plus mod T square is equals to 1. And from equation 2 and 3, mod R square is equals to mod T square is equals to 1. Thus, the equation 2 and 3 are wrong. Similarly, RT star must be equals to 0 as the commutator for A2, A3 is 0, but it is not equals to 0. So equation 4 is also wrong. Also wrong equation. So now let the, the beam splitter, this beam splitter we have used here is giving wrong results. Why it is giving wrong results? The reason is that there is a vacuum state for a classical picture. There is a unused port which do not have any changes on classically, but that produces changes when we go quantum mechanically. So in quantum mechanics, the unused port is vacuum state and it produces changes in the output. But, but classically, the unused port doesn't produce produce changes in output. Okay. So now quantum mechanically the beam splitter is this is a node cap. This is vacuum port which is absent in classical. This is A1 port, this is input, this is A2 port, this is output, and this is A3 port. This is third port, which is A2, A0 and A1 cap are input ports. A2 and A3 are output ports. Right? So, okay, for this A1 side input port, the reflectance and transmittance are R prime T prime. For this side, these reflectance and transmittance are R and T. So for A2, we can write A2 as for A2, this A1 is reflectance, A1 cap, plus T prime is transmittance, T prime A naught. A naught cap. For A3 cap, T is A1 cap plus R prime is A0 cap. Okay. So combinedly, these can be written as T prime R prime T, A0 cap, A1. Okay. Okay. So both of these equations we will use later. Use to determine commutator relation. Commutator relation. Okay. So from here, there are so many commutator brackets, but this must be equals to 1. This will give a mode of r square plus mode of t prime phi square is equals to 1 on a to k must be 0. This will give r square plus t prime phi square is equals to 0. Similarly, a a3 cap a3 cap का taker is equals to 1 will give r prime phi square plus t prime phi square is equals to 1. Similarly, there are so many commutator bracket. Due to lack of time, I am writing the direct result. So you will get one result is this r prime is mod r prime is equals to mod r, mod t is equals to mod t prime, r square plus t prime square is equals to 1, mod r square plus mod t square is equals to 1, r star t prime plus r prime t square is equals to 0 is equals to r star t plus r t prime twice t prime star is equals to 0. That is 0. So these are known as recipro reciprocity reciprocity relations. Okay. Uh, okay. So phase shift is depend on phase shift depends on making of beam splitter. For single dielectric layer, it is for single dielectric layer, it is pi by 2, which gives e to the power plus minus I to pi by 2, that is plus minus I. Right? So, taking one example for 50-50 beam splitter. So, okay. So, for 50-50 beam splitter, phase shift is phase shift is that pi by 2. So, F2 cap is equals to 1 by root 2 A0 cap plus alpha A1 cap, and A3 cap is equals to 1 by root 2 iota A0 cap plus A1 cap. Okay. Okay. So the above transmission A2 to A3 is A2 to A3 changing from A0 to A1 is unitary transformation. This can be obtained using Baker Hausdorff lemma. Hausdorff lemma, which is for that unity matrix is look at exponential delta 5 by 4 A0 Decker A1 plus A0 cap A1 Decker. This is for 50-50 beam splitter. Okay. So this the above was so this was Heisenberg picture. Heisenberg picture. Now, according to Schrodinger picture, according to Schrodinger picture, so we denote photon state as an, or this can be created. This can this can be created by applying by applying creation operator, creation operator and types and types. Okay. So okay, for zero, this is 0 0 state input state. This gives zero, sorry, two port and port input state. This is output state. This is input state 0 0 without beam splitter. When we will use beam splitter, that will change. So let's discuss one example. That is single photon input, single photon input state. That means at a single beam, at one of the input port, there is one single photon. So the input state is, let's assume at zero port, there is no photon, and at first port there is a photon. So this is the input state. So what will be the output? So we will start from this equation. So this is 0, 0 at 1, giving 0 at 2, 0 at 3. So now, you know, applying for making one photon at port 1, we will use A1 cap taker 0, 0, 1. This is beam splitter. They said same also, A1 cap taker. But here there are port number 2 and 3, so we cannot use A1 dagger. Here we have to change A1 dagger into in the terms of A2 and A3. This is simply gives and root n plus 1, the state is n is equals to 1. So this will give n is equals to 0. So it will give root 1, that is 1. So 0, this is 1 state. This is our input state. Now this is 1 by root 2 iota A2 cap plus A3 cap dagger. This is dagger 2, 0, 3. So this is after beam splitter. So it will give result A2. This iota A2 dagger will change this second port to one photon, and third port 0, plus that A3 will change second at 0 and third at a first photon, right? So this is the final output state. So what are the results? Results are single photon incident on one of the input ports of the beam splitter. The other port containing only vacuums will be either transmitted or reflected. So either it will be transmitted, that is sorry, this will transmitted, that is one photon we are getting at port number 3, or either it was reflected, so that is we are getting one photon at 2. So with same probability, reflected, reflected and transmitted with the same probability, which is 1 by root 2 pi square, that is 1 by 2, that is 50%. Okay. So beam splitter is a passive device which knows, which cannot produce or destroy photons. Okay. So there are something also, but the time limit, I cannot explain everything. So now I'm going to another example, which is so basically this state is an entangled state where we are getting one, two. So we cannot distinguish between which is for reflected wave and which is for transmitted photon. So it is an entangled state. So this is a mixed state. So it cannot be represent direct as a product of direct product of the state. So we will use density matrix state representation for that. So This can be written as root 2 3. Basically, density state is can be written as summation I 0 to infinity uh, psi I pi psi I. So that is summation I is equals to 0 to infinity pi psi I. Okay. Okay. So I was discussing that for single photon incident on if one port number one. So there is the output is an entangled state. So this cannot be written as simple state product of state vectors. So it is written in density of matrix form. That is, rho is simply summation I pi psi I outer product of psi. So for our single photon, the output is so output was let me see. The output was 1 by root 2 iota 1 2 0 3 plus 0 2 1 3. So this will be written as root 2 3 and summation. This is psi I or psi, which is this summation I pi psi I psi I, where pi is equals to half. So replacing these all values, we get root 2 3 cap. So this is an inner and outer product of the states. Okay. Uh, so the final result of this is 1 by 2 iota. This is 1 at 2, 0 at 3, plus 0 at 2, 1 at 3, being multiplied by minus iota. So this is this like here. It is minus iota. So this is minus iota. 1 at 4 is equal. It is reckoned this 1 at 2, 0 at 0 at 3, plus 0, oh sorry, 0 at 2, 1 at 3. So after solving, there will be, we are getting four terms. Okay. So, okay. So let me discuss when there when there is no detector at any one of the any one of the output port, then what will be the result? And what will be the result? What will be the result? So first of all, how we will get? So get let's suppose we do not have we do not have we do not have detector at we do not have detector at port 3. So so getting root 2, that is trace of 3 to 3, uh, that is summation as equals to 0. The detector which is unmeasured or which is not present. So we will sum over that detector, that is 3 detector and root to 3 cap for n, that is 3. So the output of this is 1 by 2, 0 root to 0 plus 1 root to, this is 2, this is mm, okay, so this is 2, this is 2. Okay, this is also 2, 2. This is also 2, 2. Okay, so what this represents? This represents a statistical mixture. There is being no off-diagonal term. In this, there is no off-diagonal terms. There is no off-diagonal terms. Diagonal terms. uh, that is a 0, 1 type term and 1, 0 type terms. Okay. So just placing a detector in only one of the output nodes yields result 0 or 1. So if we will put one detector, so it will give result 0 over 1 with each 50% of time. 50% of time. So okay. So we will get only one photon at a time. That is one photon or no photon. So 50% times it will give one photon. 50% time it will not give a single photon. So that will give zero photon. So now next example is a coherent state example. Coherent state example. Here at one of the output, one of the input, there is a coherent state. There is a coherent state. Okay, and other input is vacuum. Okay, so initial input state is 0, 0 and alpha at 1. This is input state. Okay, so this is displacement operator, which gives, or that is d defined as d alpha, that d1 alpha, that is exponential alpha a1 decker minus alpha star a1. Okay, what will this give? If we will operate it on a vacuum state, it will simply give the coherent state. Okay, so this is our input. This is input beam splitter. So what will be the output? So for output, we have to operate d1 alpha at 2 and 3. So what is d1 alpha? So d1 alpha is defined as this. So simply be writing exponential alpha a1 deca. Simply we are writing alpha a1 deca. It is again I'm sharing whiteboard. Okay. So where we were. So at output side there is exponential term and that is alpha a1 deca minus alpha star 1 pair applying on 0 and 2, 3. And the input state was 0 and alpha at 1. This is at 0. So changing A1 dagger and A1 into in terms of A2 and A3. So this is simply alpha upon root 2 alpha A2 cap dagger plus A3 cap dagger minus alpha star minus alpha A2 cap plus A3 cap applying on 0 and 0, 3. So this is after beam splitting. So uh, rearranging the terms, we get alpha by 2 A2 cap dagger minus alpha star by 2 A2 cap and similarly exponential. This is alpha by root 2 A3 cap dagger minus alpha star by 2 A3 cap applying on 0, 2 and 0, 3. So the first term this going with 0, 2 and this going with 0, 3 will give alpha by root 2, 2 and alpha by root 2. This is 3. Okay. So what are the results from it? So first of all, this is not an entangled state, not an entangled state. So this is not an entangled state, and this is result similar to classical. This is result similar to classical, where for 50-50 beam splitting, incident beam is incident beam is 50% 50% to 50% is divided into uh, reflected reflected and reflected and transmitted wave. Okay. So initially that was number of photon was alpha square. So it is reflected reflected number of photons is this is equals to transmitted number of photons, or this is equals to mode of alpha square by 2. That is mode of alpha square is equal to incident photons. So uh, it is equally divided half up into reflected and transmitted. Here we are getting the iota in reflected watts. So we are getting phase. We are getting phase of pi by 2. Phase shift of pi by 2. Phase shift of pi by 2. Okay. And the output state is not an entangled state. So we cannot we cannot obtain single photon incident state output from this result using limiting case which is alpha. Alpha is very small. Alpha is very small. But we will not get the single photon result. So the results are single photon output is entangled, as we have seen earlier, and coherent state output is not entangled. Okay, that is not entangled. So the another example. So the above example is classical example that we are dealing with quantum mechanically, but it is giving results similar to classical, and This, if we treat it as classical, this will give the same result as we are getting in quantum. So it is classically and quantum mechanically both agree. Both treatment of beam splitter agree for coherent state. So another example that is fully quantum mechanically, which is to at input at input ports, single photons simultaneously are incident. Single photons are simultaneously incident. So our input state is 1 at 0, 1 at 1. So now I am not solving the proper. We will start solving this equation to. This is the our master equation. You can see this is master equation, but I'm not solving completely. We will use a0 cap taker, a1 cap takers this side, and changing the a0 cap taker and a1 cap taker in terms of a2 and a3 and applying on this. The final result is the output is order by root 2, 2 photons at 2, 0 photons at 3, plus 0 at 2, 2 photons at 3. So as our detector cannot simultaneously count the 2 photons at once. Okay, so what this result is showing. So in single photon, the detector is not counting simultaneous photon. The reason was that the reason was that due to the particle nature of the photon. Here not measuring the simultaneously two photons at a single detector. The reason is interference or wave-like behavior of the wave-like behavior of the photon. So for uh, for the single photon, we cannot measure photon simultaneously. Simultaneously, the reason was the reason is wave sorry particle behavior of photon. Particle behavior of photon, but into incident photon incident, the region of no simultaneity is wave-like behavior of wave-like behavior wave-like behavior of interference interference of the photon. Okay, so how we can understand this? What is the happening? Like we are getting 1 by root 2 to 0 3 and 0 to we are getting this 2 photon at 2 and 0 photon at 3 at 2 photon at 3 and 0 photon at 2. Okay, so this is 2 photon at 3. Okay, so we can understand this by this is our beam splitter. So first the photon is coming, this is reflected, and this photon is coming, this is reflected. So this is A0 port, this is A1 port, this is A3, this is A2. So for A1, A2 is reflected, for A0, A3 is reflected. So first is this both are reflected. Here, this is beam splitter. Let's assume A1 is coming and it is going A3, A0 is coming, it is going A2. Means both are transmitted. but these are indistinguishable states, so we cannot different out difference in these states. Okay, so I'm gonna discuss the last point. So the last topic or last point we can say is that we are using coherent state again. Coherent state again. So the input state in that case was 0, alpha at 1. So what we can write, this is coherent state, that is n is equal to alpha is equal to 0 to infinity, alpha for n, or and root n factorial 0, that is at 1. And our output was okay, our output was at alpha by root 2, alpha by root 2. So we will write this, that is e to the power minus mode of alpha square by 2, that is alpha square by 2 and alpha square by mode of alpha. Okay, this is simply alpha square by 2 summation and barabar small n is equals to 0 to infinity, or small n is equals to also 0 to infinity. At alpha by root 2 की power and alpha by root 2 की power and divided by n factorial. This is n at 2, m at 3. Okay. So setting m is equals to n minus n, what we get is output a minus alpha square by 2 summation n over 0 to infinity alpha d power n and root n factorial psi n to 3, where psi n to 3 is 1 by 2 की power 2 n half, sorry, 2 की power n by 2. This is 2 की power n by 2 summation n over 0 to infinity alpha the power n factorial n minus n factorial complete to the power n factorial. This is n factorial. This is n minus n factorial की power half and 2 capital N minus small n at 3. Okay. So this is for the beam splitter for the transformation. So this is the transformation which is going 0 and 1. So we can see here, this is 0, 1 input state. It is going, it is transformed, the transformation is giving the result. So this is called binomial state, binomial state, where we are going number state to a fork state. Okay. So the psi n to 3 is binomial state in that n photons are binomially distributed over two modes. That's the my part. Now, the next part will describe my clips.
Good morning, everyone. My name is Ashur Jaya, and in the today's presentation, I'm going to explain about. I should explain. In today's presentation, we're going to basically talk about experimental evidence of the photon and type correlation. So there is a very nice paper by Gregor, Roger, and Aspect, which basically in this paper they basically talked about the single photon and type correlation. So we will learn in the video about that. the experimental evidence of the photon and time correlation. So let's get started. So let's start with the introduction part. So basically, as let's revise our concepts. So as we know that the classical view of the light, as the light passes from a beam splitter, we know that beam splitter. What the beam splitter does is that it basically divides the light into two parts. That's how we understand, right? One is the reflected beam, and one is the transmitted beam. So if the light behaves as a classical light, then what a beam splitter is going to do is that it will divide the light into two parts, the reflected as well as a then we will have a reflected as well as we have a transmitted part. But if we go with the quantum view, then a quantum nature of the light, we know that quantum mechanically we treat light as a photons, right? So if we deal with a single photon, then a single photon can't be broken into two parts. So either the light will go from either the light will be reflected or the light is going to be transmitted. But both of them can't happen at the same time, right? Basically, the key phenomena here is that the photon anti-correlation. We will study in the next slide what is photon anti-correlation. So, and this is basically the background. So, there was the paper was published in, I think it was 1986. Yeah, 1986. So at that time, there was no kind of no previous work on this thing, and this basically studied the previous work was studied on the non-classical nature of the light. So the main aim of this paper was to study the quantum versus the classical nature of the light after passing through the beam splitter, which of the phenomena is going to be dominant, right? So the key concepts here are a single photon state. Basically, what does it means that if the light behaves as a if light behaves quantum mechanically, then light is composed of the photons, right? Light is composed of the photons, and a single photon is an indivisible particle. Like you can't break a photon into two parts. That is, you can't if it is passing from a beam splitter, then it cannot be transmitted and reflected at the same time. And beam splitter behavior, if it is if it is behaving like classically, then what is going to happen is that the total energy will be divided into two parts, depending upon whatever is the ratio of the beam splitter, like how much does it transmits or how much does it reflects, and depending upon that, it will be done. But if it is behaving like classically, then the energy will be divided into two parts. But if it is behaving like a quantum nature, then either the photon will be transmitted or it will get reflected. Both of them can't happen simultaneously. Anti-correlation means that means the same thing. That is the no simultaneous detection. If the photon is either getting transmitted or reflected, we can't have the detection at the both of the detectors. Like after the transmission and the reflection, we will have detection at a single level, which signifies the quantum nature of the light. So this was the experimental setup used by the Gregor and his colleagues in this paper. So there was a light source, which is atomic cascade. What does it means that atomic cascade? The source is producing the photons like that in such a way that after producing a single photon, of let's say of the frequency nu1, uh, it stops for some time, and after some time it sends another photon of the different frequency. Let's say the frequency of the second photon be nu2. So what is the trigger system? The trigger system was that after detecting a photon of the frequency nu1, after that detection event, it opens the gate for the second photon, which is of the frequency, let's say nu2. And here in the setup, they had two detectors. One for the after passing through the beam splitter for the reflected wave and the transmitted wave, PMR and PMT over here, as shown in the figure. This was the experimental setup which they used. Now the measurements. Now let's come to the measurement. So the detection probabilities, as you can see that we have PMR and PMT. So the probability of the transmitted wave, like how much number of photons are getting transmitted, will be given by the number of transmitted photons divided by number of incident photons. And similar way, the probability of the reflected wave here will be given by the number of photons reflected divided by total number of incident photons. And this is the coincidence probability. That means if the light is getting transmitted as well as reflected at the same time, then the probability of coincidence will be given by number of coincidence photon. That means the photons detected at both of the detectors reflected and the transmitted, the total number of photons, NC, and divided by total number of incidence photon, which is the coincidence probability. Now, if as we know that if it's a classical behavior of the light, then PC should be very high value as compared to the other two values, right? We should have detection both of the detectors, right? But if the light behaves as a quantum nature, like if it shows the quantum nature, then we should not have the detection at both of the detectors simultaneously. That means the PC should not be a very much big number compared to the transmitted probability and the reflected probability. And what experimentally they observed was the same thing, that they observed a strong anti-correlation between them. So the coincidence photons were like 5 times smaller than it was like 5 times smaller than these two values, which confirm the quantum behavior of the light. So that means the photon doesn't split, but actually chooses one other path. That means the quantum nature, quantum mechanics wins here, right? So now let's come to the second part of the video, in which they have shown the interference with a single photon. Now we have obtained the single photon, right? Either the photon will be transmitted or reflected. Now let's understand how interference can happen with a single photon. So let's start with this one. So let's start with the introduction part, that whatever we have studied in the first part of the video. So basically, Gregor, single photon experimental setup was they used the atomic source to produce a single photon, which we have studied right now, and which they verified the single photon nature by absence of the coincidence count at the demonstrator output. And the initial setup demonstrated only the particle nature. That is, initially there was no interference, right? And now we will study how one can obtain the interference pattern using that single photon source. That single photon, I mean. Now, the requirement for the interference, as you know that if one tracks the path of the photon, then we know that there won't be any kind of interference pattern observed. And that means that the requirement for the interference is that it must scramble the which path information that must be hidden from us. We shouldn't know about the photon is traveling from like which path it is taking. That information should be hidden from us. And the implemented which is and the experimental implementation was basically they used the math generator interferometer MZI, and the like the experiment. This is the kind of experimental setup we have for the mass generator interferometer. There is a beam splitter here. These are two input states. Then we have a beam splitter 1, and here we have two mirrors M1 and M2. Then we have again a beam splitter. We have two detectors D1 and D2 to detect the reflected and the transmitted wave. And there is an additional basically a phase shifter to add additional phase between the photons. Like a photon, if a photon is getting transmitted or reflected, this is phase shifter to add an additional phase between the two of them, right? And that's what is written over here. And the operator form for this phase shifter is given by e to the power I theta n cap, where n cap is just a number operator and theta is the relative phase shift between the two paths. Here, the beam splitter is a 50-50 beam splitter. That means 50% of time it is going to transmit the wave and 50% of the time it is going to reflect the wave. And M1 and M2 are the two mirrors. Now, the single photon interference. Let us assume that the input state we sent from the beam splitter is 0-1 state. Okay. So what the first beam splitter is going to do, that it will transmit the wave or it will reflect the wave, right? So the transmitted wave is like simply given by the 0-1 state. But if the beam is reflected, then what happens is that the reflected beam, as we know that, it will add an additional phase of e to the power I pi by 2, which is what? E to the power I pi by 2 is cos pi by 2 plus I sin pi by 2, and cos pi by 2 is 0 and sin pi by 2 is 1. So in total, we are remaining with just an iota here. And this 0-1 state transforms to the 1-0 state. This can be understood like, suppose that zero photons are passing from first channel, and suppose that one photon is passing from the second channel. So after reflections, what happens is that uh, one photon will be traveling from the first channel, and the zero photons will be traveling from the second channel. And that's what is written over here. And this 1 by square root 2 is just a normalization factor. Now we have a phase shifter. Like this phase shifter is there. So that must be added. The next step is to add this additional phase shifter, right? So this state will be transformed as there will be additional phase in one of the beam, right? One of the path, because this phase shifter is along the one of the path, right? The transmitted wave, and not the reflected wave. So this additional phase will be added to the first term, and nothing will be added to the second term. So the state after passing through this phase shifter will be 1 by square root 2 e to the power I theta 0 1 plus iota 1 0. And now after that we have two mirrors, M2 and M1. As we know that both of these mirrors will be adding an additional phase of e to the power I pi by 2, and which is common in both of them. So in total, the total phase shift between the two waves will be kind of, there won't be any kind of phase shift, right? So we can ignore the phase added because of these two mirrors, because in total it is zero phase, right? Now then we have a second beam splitter BS2. So the state after passing through the BS2 can be written as, so basically these transformations are known to us. That is 0, 1, how it will transform. The 0, 1 state will transform like 0, 1 plus iota times 1, 0. After that is the reflected part, and the 0, 1 is the transmitted part. And the similar way, the 1, 0 state will also transform. That 1, 0, there is a transmitted part, and then iota times the reflected part. Uh, so basically, you can substitute the 0, 1 and then 1, 0 after passing through the beam splitter in this state over here, 0, 1 and 1, 0 over here. And then after that, what one is going to obtain is this equation. This is a simple mathematical step. One can obtain this equation. Okay. So now I would like to tell you one thing, that this 0, 1 state here, what does this 0 and this is 1 corresponds to? Basically, this 0, that is the first state over here, corresponds to, it refers to basically the beam directed towards the detected D1, the 0. And the 1 state over here, that is the second state, this state corresponds to a beam directed towards the detected D2. That means if one wants to find the probability that the detector only detected D2 fires, what one can do is that one can take the mod square of this coefficient of this state, 0, 1 state, right? This 0, 1 state. Like you can take a complex conjugate of this coefficient and you can multiply it with this term. Well, simply you can say, simply one can find that the probability of 0, 1 state, that means the probability that only detected D2 fires will be given by will be equals to 1 by 2, 1 minus cos theta. And similarly, if one finds the probability of the only D1 fires, that means this 1, 0 state, one can show that the probability comes out to be 1 by 2 into 1 plus cos theta. Just take a complex conjugate of this term and multiply it with this, well, like with the same term. And you can simply obtain that P10 is equals to 1 by 2 into 1 plus cos theta. Now, as you can see that the probability is kind of oscillating depending upon the value of the theta. As theta changes, the probability oscillates. So basically, this is how they conforms the interference fringes of the interference fringes. Also, the interference fringes with a single photon, and which confirms the wave-like behavior of the single photons also, right? And the visibility what they obtained was, which was more than 98%, and a high quality interference, right? Which was a high quality interference. And this is how the probability oscillates. This is 1 by 2, 1 plus cos theta. The blue one and this orange one is 1 by 2, 1 minus cos theta. In the summary, what we can say is that single photon exhibits the interference in the Mass-Zangen interferometer, and interference arises because, as we know that which path information was hidden from us, so that's why we observe the interference ranges. And the detection probability shows the cos theta dependence and confirming the wave particle duality. That's it. And these are the references of the paper and the book which we followed. So that's it from my side. Thank you so much, guys.
Hello, myself Kisan Prajapat, and my part for discussion is interaction-free measurement. Okay, so what is interaction-free measurement? Let's think classically. If we have object and we want to verify its presence, then we need at least one photon to interact with the object. What a photon will do? It will hit the object and come back to the detector to verify the presence. But in quantum mechanics, we can detect an object without even using a single photon. So this is a phenomenon which is first proposed by Elijah and Weidman and was experimentally confirmed by Quaid and its team and his teams. So the experiment was done. The setup that is used in this experiment was Mach-Zehnder interferometer. I will shortly call it as MZI. So first of all, let's discuss the setup. So here we have two beam splitters which are at 45-degree angle. And the hard part of the beam splitter, I am shading it. And there are two parallel mirrors which are at 45-degree angle and two detectors at beam splitter 2. Okay. कहाँ चला गया? Okay, fine. कहाँ चला गया? That will only last for white noise. Okay, so the sorry for interruption. The setup is like that. There are two beam splitters. I am shading the hard part of the beam splitters. And the beam splitters are at the angle of 45 degree. And there are two mirrors, right, which are also at the angle of 45 degree. And two detectors at the beam splitter 2. That's how the ray diagram of the MZI is here. So there are two beam splitters, two mirrors, and two detectors in the MZI setup. And let's discuss about the first setup that was done in that experiment. In first setup, there is no any object in any of the arm of MZI. And when we eject a photon in the beam splitter 1, at the beam splitter 1, it will split into two parts. I am treating photon as a wave because photon can be present at two locations at the same time. So this is the clockwise path and this is counterclockwise path. This is mirror. This is mirror 1. This is mirror 2. And this is beam splitter 7. So after reflecting from the mirror, the two waves will gonna merge at the beam splitter second, and then again they will go to detector 1 and detector 2. There are two waves in each detectors, so there will be constructive and destructive interference at detector 1 and detector 2 respectively. At detector 1, there will be a constructive interference, so there will be 100% probability that detector 1 will detect a photon. But at detector 2, there will be zero probability because there is destructive interference pattern is happening. Okay, so I'm going to discuss about in, how the interference pattern are happening here. So when the photon uh, goes on to the beam splitter one, it will split on the two directions, and either it will choose the clockwise path or it will choose the counterclockwise path. Let's say if the wave goes to the clockwise path, then after reflecting from the hard part of the beam splitter one, there will be an additional phase shift of pi. Let's say the initial phase is phi, then there will be phi plus pi phase of the wave in the clockwise path, and there will be no change in phase in the counterclockwise path. And after reflecting from the mirror, there will be also a phase shift of pi. There will be phi plus 2 pi. This is the soft part of the beam splitter 2. So after reflecting, there will be no any additional phase shift. So there will be phi plus 2 pi. And the another wave has the phase, which is the transmitting light, has the phase phi plus pi. Here the lights has phase of phi plus 2 pi, and it is reflecting from the hard part. So there will be an additional phase of pi. So there will be phi plus 2 pi. So from these two lights, we can say that the phase difference will be 0. And from these two lights, these two waves, we can conclude that the phase difference will be pi. From the condition of constructive and destructive interference, if the phase difference is 2 and pi, where n is equal to 0, 1, 2, 3, then there will be constructive interference. And if there is del phi equal to 2n plus 1 and pi, then there will be a destructive interference where n is equal to 0, 1, 2, 3. So here at D1 there will be a constructive interference, and D2 there will be a destructive interference. So at D1, the probability of any photon getting any photon is 0. Sorry, at D2 the probability of getting any photon is 0, and here at D1 the probability is 100%. So what is the conclusion? The conclusion is that if we are not taking any object in any of the branch of NZI, then there will be a probability that D1 will get a photon, and that probability will be 100%. And D2 never fires, means that it will never get any kind of photon. So that was step 1. Now I'm going to discuss about the step 2. In step 2, we are placing an object at the counterclockwise path. Now, if we impart a photon on beam splitter 1, then then again there will be a 50% probability that it will choose either clockwise path or counterclockwise path. Let's say the photon first chooses the counterclockwise path, then the material will either absorb it, or the material will reflect the incoming photon, and there will be no photon reaching at the detectors. So 50% of the times we can say that D1 and D2 never get any kind of photon. So no signal. Let's say now if the photon chooses the clockwise path, then after the beam splitter second, it will be divided into the two parts, and the detector D1 and D2 have the same probability that it will get a photon. Means D1 and D2 will fire. So 50% of probability in the counterclockwise part and 50% of probability in clockwise part. So this 50% of probability will get divided into detector D1 and D2. So when the conclusion is that when a object is placed in the counterclockwise R of MZI, uh, then the probability of getting the photo at detector D1 and D2 will be 1 by 4 and 1 by 4. So this was the conclusion, and I want to just take a look on the net conclusion of both of the steps. So if there was not any object, there wasn't any object in the MZI experiment, the D2 was off. D2 never gets any kind of signal. But if there is object placed at any of the arm of the MZI, then we get signals in D1 and D2, and the probability will be half in, sorry, 1 by 4, 1 by 4 in D1 and D2. Okay, so this phenomenon is a bit weird and seems like unrealistic, but there are few more examples that there are few examples that are given in quantum mechanics are Aharonov-Bohm effect and Bell's inequality. Basically, this phenomenon was based on quantum non-locality. And there are some real-world applications of this phenomenon. One of them is quantum imaging. In quantum imaging, we don't want any kind of exposure of light or even no exposure of light to get a quantum image. And the second one is quantum computing, in which we want to just slightly to disturb the quantum state. So no or any kind of light we don't want in quantum computing. And the last but not the least use case is explosive detection. In explosive detection, uh, that is used in those cases where the explosive is uh, much sensitive to even a single photon. So that's how we use in explosive detection. Thank you. Mm.
Hello, very, very good morning. Good evening. Myself is Napoleon. My topic is interferometer with coherent light source. Just look. My topic is interferometry. This is my topic, interferometry with coherent state of light. First of all, we see what is interferometry. Interferometry is a technique that utilizes the interference of waves to make PCS measurements, and it is widely used in optics to measure the phase shifts. And also, the frequency and wavelength of the light source are kept parameters in the interferometry. This is the basic definition of what is interferometry. And earlier we used single photon source. My friend was used in the earlier, but now here we are using the coherent state of light. Okay, and also just see why we are using coherent states. Coherent rate behaves most likely in classical light waves, and also they are easy to generate using laser and exhibit minimal uncertainty in a phase and amplitude. And quantum noise dispute their classical resemble and coherent states still exhibit quantum uncertainty. Okay, now we are using one second. So by using Mach-Zehnder interferometer, this is the diagram of Mach-Zehnder interferometers. We are using this diagram like this. So I do this. Sorry for the interference. This yeah. Second is drawing the parameters. We are using here there are two beam splitters. One is BS1, one more is BS2. Here is BS1 and this. Also here we can have a base set. This is the coherent source. We do not need alpha. Here is C and D are the nodes. We are getting output nodes. Okay, here is BS2. Earlier we looked at the interferometer using a single photon, where quantum effects were most important. Now we will explain the other example where we assume the light is in a coherent state, like regular light. Okay, in this case, the result should be very similar to what we would expect from classical light, classical physics. Imagine we are using this is a Mach-Zehnder interferometer with there are two beam filters. We are using this is the from BS1 we get this one is coherent state, one more is from BS1 input is one state. This is coherent state. We transfer in BS1, we get I alpha by root 2 and alpha by root 2 from this one. And we know the modes, like we denoting modes. A cap is denoted by 1 by root 2 under root of alpha. We denote this is this A cap plus I C cap, then number 2, one more is B, that is 1 by root 2 I C cap plus A cap. Sorry guys, we are just let's do this. Denoting its two states A denoted by A cap plus I B cap and by arm root B denoted A cap I plus B cap under root. These are the modes we are denoting. Here we are ignoring common phase shift from the two mirrors and the effect of phase shifts in the clockwise arc. That we know the identity we are using here, like alpha into alpha. Similarly, we are applying coherent state to the first mode. That should be A and alpha. It should give alpha by root 2 and A cap plus I B and alpha. We should give like applying to the this is applying here and here. Put it down. This should become 1 by root 2 alpha A cap and alpha plus 1 by root 2 alpha I B cap and alpha is equals to 0. Then this will gives, like we know this one alpha got acting here, we get mod of alpha divided by root 2. Similarly, from second case, alpha and B, this gives I alpha by root 2. This is for mod 2 and this is for mod 1. We say the mod A, mod and mod B. And we are transforming this one the B as well. We get I alpha by root 2 and alpha by root 2. One second, I have to check this one. Okay. This one, this is give the phase shift that is theta, and it will act on like I equal I theta, alpha divided by root 2 and alpha by root 2. Now second, let's first second BS2 applying Bayes splitter here. Yes. Applying Bayes splitter, not using from mode input mode. A plus 2 1 by root 2 C cap plus I D cap mode B, which gives 1 by root 2 C cap I plus D cap. Similarly, here input amplitude to BS2 is the input. To BS2 is alpha A equal to alpha equal I theta divided by root 2. Similarly, mod B, this gives I alpha by root 2. Now calculate the output mode amplitude. Here we are from here we get calculate calculating the output mode amplitude. Okay. There are two modes, one mode A, mode C, and mode D. From first we calculate from mode A, sorry, mode C. Is say that mode C equal to alpha C equal to 1 by root 2 alpha A plus I alpha B. We know alpha A alpha B. Just keep plugging here. We get 1 by root 2 alpha equal I theta divided by plus I alpha divided by root 2. After we solving this one, we get mod C equal to we get alpha by 2 equal I theta minus 1. Similarly, from mod D, we get alpha D equal to I alpha by root 2, sorry, e power I theta plus 1. So, lastly, we have BS2 perform the transformation. BS2 performs the transformation. the transformation that is alpha C and alpha A going to alpha D and alpha C. Okay. This is input. There are alpha C and alpha is the inputs and alpha D, alpha C is the outputs of BS2. Final expression we get alpha 2 equal to, after plugging all these things, one second. This one. I equal I theta alpha by root 2 and alpha by root 2 was giving we performing transformation BS2 we get here I equal I theta plus 1 alpha square divided by root 2. Similarly for alpha sim we get equal I theta minus 1 divided by root 2 alpha this one. After solving, the final output is so yeah equal to I equal I theta plus 1 alpha divided by 2 and equal I theta minus 1 alpha divided by 2. This is the final output for BS2. Now we are calculating the photon number expectation at each output. See, now we are calculating photon expectation. Photon number expectation at each output. Okay. Here we know that mean photon number is we denote n or is goes to alpha equal to equal. So we are taking for output node and C is denoted this expectation value is gives C out and C dagger psi out. After solving this one, we get alpha by 2 equal I theta minus 1 and mod cos square. Okay. On the coherent state, alpha expectation value of the number operator is we denoting like this is the only identity like we apply coherent state here a dagger a and again this coherent state is gives mod cos square of this state. So that's why we are applying the here in this case we got the this final output. And similarly for NC and D, this gives alpha mod cos square divided by 2 minus cos theta. Similar for ND expectation of ND output ND, we get alpha mod cos square divided by 2 1 plus cos theta. Now the expectation value. This is the term we want to plug in here and the expectation value is denoted O cap and expectation. This gives output ND minus NC. So here put alpha mod plus square divided by 2 1 plus cos theta minus 1 minus cos theta. It gives alpha mod plus square divided by 2 and 2 cos theta. So finally we get expectation value of rho, we get mod cos square cos theta. This is the expectation value we got. The uncertainty phase measurement is given by we know now we are going to find uncertainty measurement for coherent state. The uncertainty of phase measurement. Phase measurement is given by delta O, sorry, this is delta P. Delta D is gives du divided by derivative of expectation value with respect to theta. We found this and also where delta O is gives grouped under expectation value square square minus O expectation of the whole square. This is the we got delta O. And also we differentiate with respect to the expectation value, it gives minus alpha square sine theta equivalent. So you know, we plug in this equation, we differentiating on the side by the expectation with respect to theta, we give minus sine theta alpha cos square and more. This is more explained to alpha cos square minus theta u. So we plug in here, and also we know that delta of theta equal to root under n, where n is the number of photon number is equal to the mean. This is the photon number. This is where n say that photon number that is equal to mean. So therefore delta theta equal to n divided by n comma sin theta comma, it gives 1 by n sin theta comma. Here is first uncertainty phase measurement. Here the minimum uncertainty we got here is theta equal to odd multiple of pi by 2, like n, here n equal to 1, 3 and 5. It gives minimum space uncertainty. Is anything. So that should be the theta minimum. This gives equal to 1 by this is the range. Okay, don't need. Yes. We got here is a graph between this is the graph photon numbers versus phase uncertainty. It is phase uncertainty. Thank you for the correct engagement. This part should be like exponential decay. We got this is like a graph from phase number and uncertainty. This is d theta minimum equal to 1 by root. And here, if minimum phase uncertainty is increases, d theta minimum and number state it goes to decrease. So this is the my part. Fine, this is my part. Thank you. Thank you so much.